Okay, so today we're starting to now. Well, we've already started turning the corner, but we're going to now start turning harder. Um, I want to talk about this idea of parsing. So when I say parsing, what does that mean to you? When we parse a program, so we take some Java code. So we have our Java program, and we parse that. What are we doing? What does it mean to parse something?
Search through it and like extract data.
Okay, I think we're going in a good direction there. Okay, what do you mean by extract data? What are you trying to do when you're parsing?
You have like a search, like they user input something we want to search for, and it goes through and looks for that specific key.
All right, when we look at a Java program, can you tell what that program's doing? If you look at it for several minutes, you kind of walk through it. How do you do that? How do you figure out what that program is logically doing? Okay.
Going line through line.
All right. So you're kind of attaching meaning, attaching semantics to each line or to each or some groupings of lines, right? You kind of see a for loop and immediately you think that's gonna repeat some stuff, right? So you're semantically saying this chunk right here repeats some stuff. Now, what does it repeat? That's going to be the contents of that. So you are in effect parsing through that program, adding semantic meaning to the various pieces. All right. Now, for a short program, you can kind of memorize that, right? Just kind of think about it and say, oh, this is what this guy does in the big scheme of things. But now, would it be beneficial for you to then take that and convert the Java syntax into a data representation? So you talked about extracting data, right? So turn it into a data representation based language, which kind of marks it up, add some semantic information. Sometimes it's referred to as metadata. Add some stuff to what's already there. Sometimes it actually makes it bigger. In fact, in many programming languages, it probably does make it bigger. But what it does is it allows us to semantically identify um, something. Okay. So, for example, let's kind of just give let's say this is convert a program from its initial state into a data representation language. You would probably never find a book say it that way. But since I've used that phrase many times, I think we all know what data representation means. I've referenced like scheme, or XML and JSON, that kind of stuff as data representation. So turns it from its initial state into a data representation language, which carries meaning or semantics, something like that. And we'll look at an actual example here in a second. So that would be kind of our big pie in the sky type thing for it. So as an example, if I had, let's just look at a lambda expression. So if I have a lambda, well, we're going to get it third time's a charm. So let's say lambda x plus a b. So I'm expounding this a little bit some more in the scheme world. Maybe we turn this into a lambda exp. I'm just throwing some stuff out here. Param, actually, maybe we call this guy, let's call it params symbol x app expression plus expression. Let's just do plus exp. Symbol a symbol B. Closes that closes that closes that. All right, something like that. You know, we can, when we actually write a parser and unparse, we'll pick a final format. But, you know, certainly this is now bigger than it used to be, right? What's the advantage of doing this? What have I, so I've added meaning. I've marked this up. So for us, when we look at this line, we can, as a human being, we can identify that pretty easily. We are very good at things like this. We can glance at some code like that and say, oh yeah, that's a Lambda expression. You know, we're kind of looking at all the pieces of it all at once, and you know, if we spend a little bit of extra time, we can kind of like certify it and say that that's a legal Lambda expression or something. But humans are good at stuff like that. Computers are not as good. What's the advantage of turning something like this into something like this? And why would we do it? When we write a program, what's our ultimate goal? Why do we write programs? To solve a problem, because ultimately we want to run the program, right? So at the end of the day, we want to press the play button or whatever and go, have it run. All right, so you know, at least I never didn't get the thing because that's what the homework said to do. That's why we wrote the program, because the homework said to write the program. All right, so ultimately we want to run it. So we have to think about what's it going to take to go from a language representation, Java, Scheme, C#, whatever, pick your language, into something that the computer can then execute. And then on that execution side of things, we have some desires, right? We want it to be fast, or at least relatively fast. You know, certain languages are going to be faster than others. That gets back to the whole compiled languages versus interpreted languages stuff. But certainly we have an expectation of speed, you know, for our computers, with the understanding that our computers are really fast, so we can kind of take advantage of the overwhelming speed of our computers and maybe be a little bit more human friendly on the other side because our computers are so fast. So we ultimately want our program to run. So would it make sense for us to maybe make an initial pass through our program and put it into a format that might kind of stage it so that it can run more efficiently on the computer when we actually hit play? That would make some sense, right? Now, having said that, do you think a computer, especially our modern day computers, for you know, your average computer program that just is solving some relatively small problem, could it probably just do all of it on the fly and we wouldn't notice? Probably. It probably could. But we're certainly not hurting anything by doing some conversion up front, right? Putting it into a situation where it can run more quickly. And we think about the difference between interpreted languages and compiled languages. So compiled languages, we do that conversion way up front. So when you download a video game, that conversion happened back at the software development company. And what you're getting is an already parsed, already compiled program that's now been reorganized into a set of magic tricks, a set of instructions that it feeds to the CPU. And decisions are made off of that. Okay? So the advantage of moving it into something like this is we have now removed many of the decision-making things. Okay? So for instance, if we pretend like we're the program that's determining, is this guy a Lambda expression? We've written that several times already, right? What are we doing? We're looking, well, is it a list? Is the car of the list the word Lambda? Is the catter of the list a list containing a symbol? You know, we can take it as far as we want to take it to validate the thing as being a Lambda expression. But we can appreciate the fact that that is effort, right? Now, does determining if it's a Lambda expression have anything to do with processing a Lambda expression? Those are two separate sides, right? Once I know what it is, now what do I do with that? That's the other side of it. So parsing allows us to solve one half of the problem initially so that we can focus on the other half of the problem after the fact. Okay? So when we say parse expression, when we turn something from something that looks like this into something that looks like this, we are parsing that And right now our language is the language of Lambda calculus expressions, our simplified version of that, right? We're going to expand on that relatively quickly here, and then throughout the semester we'll keep expanding on it. But we have a simple form of that language. So when we parse that, we're turning it into, from something that fits the definition of the language syntax, into kind of a marked up version of that. So that all we need to do to determine if this is a Lambda expression, we know that every single thing we're dealing with is going to be a list. It's a list that describes what's in it. We just have to look at the car of the list. What are you? I look at the car, I'm a Lambda expression, done. Now I know what to do with you. And then you throw in the logic of actually taking out the pieces of that Lambda expression and working with it. That makes sense? Now, as an exercise, we're also going to write unparse expression, proving we can go back the other direction. Turn it back into the actual program. Decompile the program if you want to think about this in kind of generic terms. Okay, so, and we'll make some decisions of what our parsed and unparsed versions should be. So let's go in here. So we're going to say define parse exp to be a lambda that takes a, I will say LC expression as a parameter, just to specify that what that guy is actually going to be. And we want to turn it into, a marked up version of this. Okay, so we're going to use our normal pattern, our cons and stuff like that. So we're going to have our con. We're going to ask, is this Lambda calculus expression, is this guy just a symbol, right? So if this guy is a symbol, let's get our book up here. Bring up our, probably go down a little bit. I think we have, yeah, here we go. Oh, they actually given us an example of this. Okay, so we have our Lambda calculus expression. So if we're looking at something that's just a symbol, we want to turn this guy into a var expression. All right, a var expression that contains the variable. Okay, so if I'm looking at this production of a Lambda calculus expression, I'm going to turn it into, and we're going to make this list-based. All right, so I'm going to turn it into a list whose first element is var-exp and whose second element is the actual variable. Okay? So that means this guy, if I'm looking at a symbol, would become the list var-exp along with LC expression. And actually what I'm going to do is we're going to use our list constructor for that. Like that. So that's what that would produce for a the var expression form of our Lambda calculus expression. All right. Otherwise, if I'm not a symbol, I must be a list by our current definition, right? So I'm either the app expression or I'm the Lambda expression. But I know I'm a list, so I know I at least have one element. We're not going to do any error checking here, just so we can focus on the parsing and unparsing aspects of this. All right, so now I'm going to say EQV lambda car LC expression if I'm looking at something that is a lambda. Okay, if that's the kind of dude I'm looking at, then I want to convert that guy into a lambda expression that contains a bound variable and also contains the body. Okay, so list containing 3 elements. Who? Lambda. Nailed it. All right, so if I'm looking at that kind of animal, what am I going to do? I'm going to create a list containing, now, one thing I'll ask here, do you kind of recall when we were doing all those like little trivial, well, I say trivial exercises, kind of the first month of class, didn't we do something sort of like this? But it wasn't really put on us as if we were dealing with parsing, right? Oh, we were replacing elements with some names. I think it might have been a binary tree thing, like putting leaf in front of it, stuff like that, right? Because we were creating a parser. Didn't really, that wasn't, the other side of the coin wasn't shown to us, right? All right, so if I'm looking at a Lambda expression, I'll create a list containing Lambda exp along with, now I'm going to be a little bit more, expressive with this just from the perspective of really driving that home of variables being bound. All right, so it might end up looking a little different than what the book says. So I'm going to actually create a bound variable list. So this guy's going to contain, well, let me think about that. The reason I'm going to do this is to kind of be prepared for what's happening next. Eventually, you know, we're going to have Lambda expressions that could take no parameters as well as Lambda expressions that could take more than one parameter, right? So really what we're dealing with here is a parameter list. So I'm going to create a list called bound vars. Actually, for right now, just so we don't confuse ourselves, let's call it bound var. But before long, we're going to be adding an S to that. And if we have no bound vars, it will be a list containing only the word bound vars. Okay, so this guy would be a list whose first element is bound var, whose second element is actually the bound variable of this guy. So if I'm looking at a Lambda expression, I need to get the catter gets me this list. The CAADR gets me the identifier. That makes sense? Now, the reality is we want to make this kind of generic for moving forward. If I'm going to have my bound vars moving forward, what can I do with this list to incorporate it in its entirety into this list? So if I have a list that contains just the word bound var, and then I have another list that contains a collection of variables, a collection of symbols. Right now, that collection of symbols is always going to be exactly one symbol as a collection. How can I glue those two lists together? Which of our list constructors lets us take two lists and put them into one list? Append. So I can come in here and I can say I'm going to append the list containing bound var onto the catter of LC expression. Now, how else could I have written that same thing? So we can practice our, what I have highlighted there, I want to rewrite that identically using our other list constructor, cons. How could I write that with a cons? So we are practicing the difference between append and cons. Somebody who usually doesn't speak, preferably. And then we'll fall to the secondary audience. So what I have highlighted right there, I want to rewrite that with a cons instead of append, but have it say that it ultimately have the same output. Go ahead. You do usually speak, but less so than some of the other people. All right, go ahead.
Just remove the list from the bound var.
Okay.
Because a catter, and also cons the catter to them.
Won't the catter be a list? Isn't this the car of the cutter? It's already a list, right? Yeah, so we don't actually need to do it on an empty. It wouldn't have hurt anything. Just would have been extra stuff. So in this case, we're going to cons. We're constructing a list whose new first element will be this element, which is just the symbol bound var. And the rest of the list we're adding to the front of, is this list, the list that is produced by getting the catter of our LC expression. Make sense? So those two things did the same thing. this is probably the better way of writing it. Why wrap something in a list if you're just going to glue lists together, but at least allowed us to illustrate the difference between append and cons. So that's going to become increasingly important for us, as you might guess, as we're putting lists together and taking lists apart. It's going to be a tool that we're going to use pretty often. Okay, so if we're looking at a lambda, we're going to create a new list whose first element is going to be lambda expression. This is the metadata describing, giving semantic meaning to what we're dealing with here. And the first element of that will be the bound variables. The second element of that will be the body, which is an LC expression. So do I put in the CADDR of LC expression here? Tell me why that's wrong. What is the CADDR of LC expression? Is that the body of our lambda expression? Is this the car of the critter? Yeah, it is. Why is it wrong to just include it as is? So if I just do that, and that's the end of that condition, why is this guy right here not representative of what I actually want it to be?
Wouldn't it just give you the first element of the catter? It would be the first element of the body.
Well, the body is an element. This is just one element. It could look really scary, but it's one element that is a lambda calculus expression.
Which could be a variable.
Could be a var expression, could be a lambda expression, could be an app expression, could be all sorts of things.
Because the expression needs to be parsed.
That guy's got to be parsed. Otherwise, I'm going to create this like weird Frankenstein thing where I have, the top level parsed, but things that are inside are never going to be parsed, right? So I'm going to have to take this lambda calculus expression, this guy right here, and I'm going to have to say, okay, I want to parse him. And what does parse expression know how to do? It knows how to parse a lambda calculus expression. So we'll call parse exp on that guy. And I'm going to go ahead and kick these things down a few lines, if you will allow me. I think that becomes a little bit easier to read. So I'm going to create a list containing lambda exp, containing a new list built with bound var at the beginning of it, and then the rest of my bound variables. And then creating whatever, the third element of this list will be whatever parse expression returns for the body of this lambda expression. Fair enough? All right. Now, for us right now, we only have one more production for lambda calculus expressions, even though we're pretty sure we're going to be adding some other things. What other things, just out of curiosity, since I'm sure most of you have not looked significantly further ahead in the book, how many of you have read the whole book at this point? Like, what are you, nuts? I haven't even read what you've told us to read. What other things might you expect us to bump into in our language of lambda calculus expressions moving forward? If we fast forward 2 or 3 weeks, what other expression types might we see? Think about programming languages. Think about Java. What's a var expression? That's us defining a variable? Okay. Well, actually, that's us using a variable, not defining it, but using a variable. What's a lambda expression? It's a function, right? Writing a function. We haven't really, associated it with a variable yet, but it's a function. It's a representation of a function. What's an app expression? Kind of talked about this, I think, last class. Where I said, what if we were going to call one of our functions and pass it some inputs? What's an app expression? It's how we call a function with parameters, right? Is that all we can do in our programming languages? Call functions? It's one of the things we do. What else do we do in our programming languages? If we go back to the 3 ways human beings solve problems, what's number 2? We remember stuff. What's number 2? Something and then repetition. What's number 2? Ask questions. Okay, ask questions. How do we ask questions in our programming languages? Conditionals, usually if statements. So you think we're going to have an if expression? So if expression will have 3 parts. A Boolean expression. What happens if it's true? So the true expression and the false expression. Might we have some expressions for representing loops? We have a for expression or a while expression. So can we kind of we can keep going down that list and keep adding stuff to our language here, right? So you kind of see where this is going. All right, so we're really dealing with a very tiny piece of our language here. All right, so right now we only have 3 productions. The 3rd production is our app expression. So we'll throw an else in here. So else, we must be dealing with an app expression. So what are we going to do? We're going to produce a list containing app exp and then containing parse exp on the car of lcexp along with parse exp on the catter of lcexp. So I'll do what I can do at this point where I'm going to say, oh, I've identified this dude as an app expression. So I'm going to go ahead and I'm going to boil down to a list whose first element is the word app expression, whose second element is whatever parse expression returns for the operator, and whose third part is whatever parse expression returns for the operand. That makes sense? So is that parse expression? So we can test this guy. So if I define exp to be a lambda that takes in a x and returns let's just throw some stuff in here, an ab, what would we expect the result of this to be? So this expression, what kind of expression is this guy? Lambda expression, so we'd expect this guy to spit out lambda exp, so this guy, followed by a list containing bound var, followed by x, right? So that, followed by whatever parse expression returns for this guy. What does parse expression for that guy return? Well, is that guy a symbol? Oh, the list AB is not a symbol. So it must be a list. Does the car of that list equal lambda? Nope, so it must be an app expression. So this guy's going to return a list, app exp, followed by whatever parse expression returns for the first part of that list, which is this guy. What is parse expression going to return for that? This guy right there. A is a symbol. Since A is a symbol, we're going to return a list containing var expression and then whatever the LC expression is. It's got to be var exp A. B will be the same thing. Var exp B. Is that what it should return?
Up top.
It's where you left that error last time that we were going to.
Oh, the occurs bound helper. I got you. Let's just can I do a multi-line comment on this? Let's just do this.
We didn't finish that.
That's okay. It's not a big deal, right? We were pretty close to being done. You want to finish it at some point? Is that what you're saying? Okay. So then I need to just comment out these lines, and then will it stop screaming? Or have I called that in other places already? Oh, here. EXP LOL. There we go. there we go. Oh, we actually need to call our function on this too. So now we're going to call parse expression on EXP LOL. And that should give us our parsed output. Oh, it is calling it. Let's just throw a curs bound up here for right now. Actually, let's comment these out. All right, there we go. So we get a lambda expression, list bound var x, list app expression, list var expression a, list var expression b. Okay, so that gets us our output of that guy, right? So now if I copy that, and then I go ahead and I do define result. Actually, why should I write that in there when I can say define result to be the result of parse expression on that stuff. And then I can go ahead and print out result if I want. So I'll run this again here. All right, so there's my result right down here, but I've stored it inside of a variable. So I define result, set it equal to whatever parse expression on EXP_LOL returned. And then I printed out result right there. So now if I want to go and unparse result and get us back to something that looks like this, this would be unparse expression, right? So define unparse exp to be a lambda that's taking in a, now this isn't taking in an LC expression. It's taking in a parsed LC expression. So let's call this guy a P LC expression. It's a parsed one, okay? And now we're going to do some cons based on the types of things we can run into. So I'll have a cond. Now I know every single element I'm looking at in here will be a list. So I'm guaranteed to be working with a list. So very first thing I could be dealing with here is that I might be EQV car PLC expression is var exp. If it's one of those dudes, what do I return? Here's my var expression. The car is this. I want to just boil down to this, right? I want to extract that var from it. So I'm going to boil down to the catter of P LC expression, like that. Otherwise, if EQV car PLC expression is a lambda expression, I'm going to boil down to a list containing lambda. Then I need to go ahead and pull out the variables from my bound expression. So I actually want everything but the car of that guy. So it'll be the cdr. So I want the cdr of the catter. So CADR will give me the list containing bound var and a bunch of variables after it, right? And I want the cdr of that guy. Cadatter. It's a fun one, right? And I want the cadatter of that guy. So P LC expression. And I don't need to unparse that, right? That guy wasn't actually an LC expression. He was a representation of it. But now the body of this guy is an LC expression. So then the last thing I want to do is I want to return whatever unparse exp returns for the CADDR of this guy. CADDR of PLC expression. So that's the list I'll return there if I'm turning it back into a normal LC expression. Else must be the last type we have, which is an app expression. So if it's an app expression, what am I going to return? I'm going to return a list containing unparse exp on the car of PLC expression, along with unparse exp on the catter of PLC expression. And then what we'll do is we'll go ahead and we will say unparse exp result, which should get us back to our original. Car expects the pair given an app expression, so... Oh, I need the car of the cooter there because I didn't peel off the app expression. And then the car of the cooter. So there's our lambda x list AB. So we've parsed it and unparsed it. Does that make sense what we did here? Because we were in the else, I still had a car that was app exp. I had to peel past that and just get the car of the cooter of that guy, which was the actual operator, and then the car of the cooter, which was the operand. All right, so this is parse and unparse expression. Okay, and they did something similar here, but you know, I like ours. Ours is pretty close to that. Okay, so you can actually see right here, we're going to start talking about this, well, we'll talk about it officially later, but we have this thing called cleany star. So here's a version of that lambda calculus expression where we have 0 or more identifiers in our body. Okay, so go ahead and give this to you now. So for homework, I want us to look at 2.31. So this is actually taking something that we just did and doing it for kind of an unfamiliar language, small language. So we have this thing called prefix list, and this is for reverse Polish notation. If you're doing if you've ever used a calculator, like an accounting calculator or something like that. So sometimes it's useful to specify a concrete syntax as a sequence of symbols and integers, surrounded by parentheses. For example, one might define the set of prefix lists as a prefix list is a list containing a prefix expression, where a prefix expression is an int, or a prefix expression is a minus followed by a prefix expression followed by a prefix expression. So, for example, this list right here is a legal prefix list. That is, it's a minus followed by a prefix expression followed by a prefix expression. That's the prefix expression followed by a prefix expression. The first prefix expression would be another minus list, that guy. The second prefix expression would be this guy right here, where the first prefix expression would be the 4, the second prefix expression would be the minus followed by the 12 and the 7, whose first prefix expression would be the 12 and whose second would be the 7. That's this production right here. All right, so this is sometimes called Polish prefix notation after its inventor, blah, blah, blah. Write a parser to convert a prefix list to the abstract syntax. Okay, now I already mentioned before that we are not using data types in here. So you can forget about this version of this and think about it in terms of lambdas. You know, writing a normal scheme lambda functions. So that the example above, so for instance, if we pass it, think of this like our lambda calculus expression. Okay, this is something that is in the legal language of a prefix list. So what I have highlighted there, is to a prefix list as what I have right here is to a lambda calculus expression. Does that make sense? So two separate languages. One is the lambda calculus expression language. The other one is our prefix list language. This is an example of our lambda calculus, of some legal syntax in our lambda calculus language. This guy is an example of legal syntax in our prefix list language. So if you were to take in something like this, and you wanted to parse that into something that produced this, that is, we have a diff expression, followed by a diff expression, followed by a const expression, diff expression, const expression, diff expression, const and const. Make sense? So what I want you to do for your homework is write a parser and an unparser for 2.31. Parse list, prefix list, and unparse prefix list. Do what we did in class today to go both directions. Yeah.
You want us to use diff expression and const expression, or can we name it something else?
Well, I mean, you can name it something else if you want, but if you want to compare your results to what their output is, you might as well use those. Because diff expression and const expression are just these decisions. That or that. You know, we're deciding how to mark it up. So you might as well call something that starts with a minus a diff expression, and something that is a number a const expression. I don't think it's going to hurt anything to do that. Does that make some sense? All right. So somebody next time try to remind me, if I try to start doing it right now, then we'll just run out of time again. Try to remind me to finish that helper flippy dealy thing from last time, and then we'll look at the solution to this. The Bible homework is already up. I put that up yesterday somewhere, so that's due on Friday. And then this will be due on Friday as well. So it is exercise 2.31, but I want you to write parse and unparse. So it's a little bit more than what 2.31 just asks for. Everybody clear on that? All right, I will see everybody on Friday.